Let's start. Hello. So your mixer demo is next week. I postponed it by a week. It will get time to settle down after a long break. So, and you must have noticed on the backpack, we will look at 3 components. The first one is how much amount of work you have done. The first thing is quantity of work. So this basically means if you have, you envision the project, how much you have achieved so far. So you submitted a project proposal which we have evaluated, we'll see in the feedback very soon, but for some of you, you had some vision, but when you started implementing things, you realized these things don't work out, or this thing works out better in some fashion, right? So let me have a change in direction and improve on that, right? So overall, it's not your project proposal that we will always compare it with. Right? If you say, okay, in the proposal I said this and I have done, right? So you should give me full marks. It doesn't work that way, right? The reason is because for some of you, some things have changed. For some of you, what you wrote in the proposal is too less, right? And so finally, we will see how much work you have done. Right? So you should first focus on the things you have done, things that are over, finished, right? And things that are remaining. You should talk about both. Then another thing is what I say, robustness. Right? So a lot of you think about very nice things to do, right? Lots of components. But every component that you build is actually, it's very flaky or flimsy. And I mean, you say, okay, I will connect to the internet, I will download this, and then I will look at the sensor, I will get the accelerometer data, and then all that, right? But finally, nothing really works. Right? And so you make a mistake, not a single one really works out. Okay, so we want to see which things you have implemented. It's not just the quantity, but the quality also matters. What you have done, how good it is working. Right? So that's the second point. Of course, we will not be able to test it out fully, but we can see, I mean, the things that you are doing are trivial or not. And the third thing is what I say, innovative. See, some projects do a lot of work, everything works, but they haven't really stretched. Right? If you connect to a database, right, and you write simple forms and you store, right, retrieve back. So it's a lot of work, right? It works also very nicely, but it's not something where we have tried something very hard things. I'm not saying everybody has to do something innovative, but if somebody has done, then it would be good if you highlight it at the time of the demo. And this thing there, and this was a challenge. Or I didn't find anything in the open source community or any library which could easily do it. Or this sensor, I was collecting data, but there was a lot of noise in it, and I had to compensate for that, and that took me a while, right? So this is the third dimension. And these are the things which are risky, challenging. You need to think about it, right? But at the time of demo, you should be able to bring it up, right? So I would like you to think in all these three things together. When you give a demo, it's not just showing what you've done, but you should also talk about where it stands here, where it stands here, and where it stands here. Questions? So this is our scale, and this scale will be given to TA also, and I already shared it with you. We will evaluate everything on these three dimensions. And one could be very good here, but not so good here. And one could be good here, but not so good here. And one could be good here, but not so good here. Right? So depending upon where you have excelled, we will give you marks there, and there could be projects which could be better on all the three dimensions. Now, you can ask me questions about this. Not specific to your project, because I can't discuss every project where it stands where now. Right? But overall, what do you think? Is this three-level scale?
What form does the demo have? We just give you our app and you will try it? Or
No. So you bring your device or your simulator. Okay, so there will be two groups sitting there. There are offices there if you visited the third floor video. Right? There are some open offices there. There will be two sets of keys, 4. Right? I don't want one key to look at your demo and decide the full marks. Right? There will be 4 keys who will look at least 3, maybe at a given point in time, not all 4 there. But at least there will be 3. All 3 of them will look at it. Right? They will have the opinion on these 3, right? And then they will discuss among themselves and have a consensus. Right? So it's not like if you get bad marks because of the mistake of one team. Right? All 3 look at it and they say, okay, this is bad, right? So we will go by the majority. Or the consensus, in fact.
So that's it.
Is it okay? You will get 5 minutes.
Okay, so we just talk for 5 minutes and then we get it.
So we show the working thing also. Right? Most important is not just talk. If you just talk, right? You can talk very nicely, I know that. Right? And then the PAs, you just go by, there is no demo there, right? You just record the audio and send it. Right? So you have to show it really. Whatever you talk, you have to also show and tell. You also show all these things.
Considering that the English is currently in alpha,
Yeah.
so judging robustness of the application will be questionable.
So we will judge it at this level. I know. So this is the final thing, robustness will be far better. So you might have, whatever you have developed, right, that could be robust. It's not full. Right? But if you have done one thing, right, we can check robustness of that one thing. And you also have an option where you just don't think about robustness for now. This is not the final demo. Maybe, right, you sacrifice right now everything here. But at the final demo, then you have to better bring it up.
For example, if a project is driving from technology that
Yes.
so
Yes.
probably it will take them some time to
Yes. Yes. So you will score here and here probably, not here. But that's your thought, whether you want to do it or not. Right? We want to encourage all these 3. Right? And if somebody has done here, good, very good, we also want to give some points there. Right? Because otherwise it becomes hard to evaluate 2 different projects. Question? Yes. No. So at this point, we will not go into individual cases. Like how much contribution each member has got. That will come at the end, which will have impact on the rates throughout. Right? At the end, I am going to ask. See, somebody might have done more right now, right? Will do less, or vice versa. Right? So at the end, we will see who has done how much throughout the project. You can do that if you want, but it's not compulsory. For some of you, you create slides, you know what points you should talk about, right, and you present it back. But make sure that you should be able to finish within 5 minutes, right?
So all the team members should be present.
Yes, yes. See, first thing is the class time, so I don't think there will be a clash. If you've taken this class, and you should have free time at that point.
What is the weightage of this? The
Alright. So that I'm not disclosing right now, right? But typically it has substantial. So overall it's 35%, right? The project. So this will be about 15, around 15 plus minus. And it's significant. It's not trivial.
that means things after can change after time.
No, I'm not going to commit it right now, right? But I'm saying it is 15 plus minus. Maybe it is 15. I might reduce it. See, I have to see how much. If not, see, all of you have not done anything, right? This could happen. Then if I give it 20% weightage, what it will be, right? It doesn't make sense. But I want you to do something. So that's what I'm saying. At least I think it's about 15%. And so remember another thing, it's 5 minutes, right? The hardest part for me, I think, if I am the student, it's presenting everything in 5 minutes. See, if you talk about very simple things, in 5 minutes, you lost your time. And you might have done something very nice, very good, but you ran out of time. And that's the reality of life also, right? Nobody will give you infinite time. So prioritize things. What do you want to talk about and show at that moment? If you have, a lot of times I see people show the login screen, and that takes 5 minutes. And then when the real app works, I mean, who has time there? Like you say, okay, it's done. So you should prioritize things in your mind. What do you want to show? If you are given 5 minutes, every presentation, even today, right, I have 40, whatever minutes, 90 minutes. If I just talk about my first slide for 90 minutes, right, I have lost my time. Not unfair. Right? This is the reality. You should think about you have 5 minutes and what do you want to talk in those 5 minutes. It's your chance. If you talk about simple things, right, you can not get good marks. But if you talk about the important things on these three things, then right, get better chance. Other things, as one thing is we haven't given micro level schedule. Like these 5 minutes, this group, this 5 minutes, second group, right? But so you have freedom there. Within those 3 hours, you can come any point in time. But if everybody of you come at 5 minutes before 5, and you say, I mean, there will be one group, and if you're not that lucky group, right, you miss your chance. You miss the deadline. Okay. There will not be.
You will define that order, you will not define that order.
We don't define that. It's 3 hours, it's your call. Whenever you feel comfortable showing the demo. See, there are some people who start working right at 5 minutes before. Right? They will come at 5 o'clock, I know that. Right? So that's why I'm not scheduled anything. Okay, you decided, it's your call, right? But if you come early, your chances of getting finished before 5 is better. So that's also your call. Other things? So let's come back to the wireless part again. So I have posted solutions for the last assignment. It's already online, and the TAs will now grade it and get back to you about it by this weekend. So I showed you one set of slides, and there was another set of slides which I posted on Backpack. But I'm going to go through it anyway because These are important ones, and the PowerPoint does not have all of them. So CSMA CA is different from CSMA CD. Does anyone remember what is the CD part and what is the CA part? So the CD part is collision detection, which happens on wired network, where you can detect a collision at real time. And in wireless, because you can either transmit or receive, you cannot do simultaneously both the things, and you cannot detect a collision at that time. So you just want to avoid it as much as possible. So the protocol is basic protocol of CSMA is the same, but there are mechanisms built on top to avoid collisions as much as possible. So this is not a distributed coordination function. This way, when we do 802.11 Wi-Fi, it's all distributed. Right? There is an access point at the nodes, right? And everybody, the protocol says everybody is on the same line, same priority. And access point also competes for the carrier or the channel, and the stations and the nodes or the clients will also compete for the same channel together. Right? So that's why it is fully distributed. So far, I haven't said anything where access point gets the priority, and it can use channel as much as it wants. Right? That's not the case here. Everybody is competing for the channel. So that's why this is called distributed coordination function. You know all this? So node listens to the channel before transmission, whether anybody else is transmitting. Right? And after the successful transmission, there is an acknowledgement also, which is after a short time interval. Every two data frames have a long duration in between, and between data and act. Right? So between two data, right, there is a bigger duration, and between data and act, there is a shorter duration. Right? So this in a way gets priority. Acknowledgement is getting priority over data because it doesn't have to wait that much. Every node sends an acknowledgement after a short period of time. If acknowledgement is not received, that means either the data is lost or the act is lost. The sender cannot differentiate between these two. Right? It says something is bad. Right? So packet is considered lost. Right? That means it is equivalent to saying the packet is lost and the retransmission is arranged. Right? And then the data will come back again. Right? So this is fully distributed and it works this way. Then there is another mode which we say RTS CTS. What problem it deals with? What is hidden terminal? Right? So there are cases where you can, if you just fully depend on DCF, distributed coordination function, but the nodes are arranged in the environment such that there is one node which is hiding, like two nodes which are hidden from each other. In that case, you need a better way to get out of this situation, and that's where you use RTS and CTS. So the way it works is if the median is busy, the node defers to transmission. Back here. So can you remind me what is RTS and CTS? The protocol exchange.
Send the request to send
AP?
to the AP and AP accepted, send the clear to
Right. True. So RTS message contains some time value. It says I want to reserve and I want to request channel for this much amount of time. The access point is okay with it, it says clear, right? And then every node in that circle will not transmit anything till that time duration is over. Right? And after the act comes back, then the data transmission can begin. Okay? So that's how you have two ways of doing it, without RTS CTS and with RTS CTS. And within the distributed coordination function, you have a window or a contention window. And this contention window CW is between this 0 and W minus 1. And the size of this window increases as we have more and more losses. So if you see there is a transmission loss because you did not get back. wait for a longer time, and will keep on increasing till a maximum value. So the protocol, the details of the protocols are not in that slide, but it's here. The median is sense, or it should be idle for DIFS amount of time. At any point when you transmit, it should be idle for DIFS before that. If you are doing a back off and you're counting down, and if a transmission occurs, what do? So I have backed off, and I have my own timer, which will expire when it reaches 0. And in between, I sense somebody transmitting. You pause. You pause your timer, right? You don't want to run it out, right? And then, because the transmission can be longer, and you run out of it, and then what do? The channel is already taken, right? But you don't also want to reset it because that will delay you long. So what you do is you pause it till all the transmissions are again gone, right? They're finished, and then you restart that time. And finally, when it reaches 0, the station is ready to transmit. Right? And if the collisions are occurring, then the initial value of CW is 1, and keep on doubling it. It's an exponential back off. Right? That's how you increase very fast. If the source node does not receive an ACK due to collision or transmission error, it deactivates its backup algorithm. Right? So whenever you don't receive back an ACK, right, you activate the backup algorithm, you expand its size, right, and that is how you delay your transmissions. Yes, SIFS. So this is DIFS. And this is, it's a constant time value.
It should always be less than 0.
This will be less than 0, and we saw the reasons. We saw a reason for this. Right? It has to be less than this. In fact, DIFS equal to plus SI. No, it cannot be plus. It is plus something. But it is greater than or equal to twice. Okay, so DIFS is greater than or equal to twice the SIFS, at least twice. Okay, so these are derived from RTT. Right? There is some relation between RTT and this. Okay, so. But every node is programmed with this one. Your Wi-Fi driver has this hard-coded. So there are two ways of doing carrier sensing. One is the real carrier sensing when you listen to the channel, and one is the virtual carrier sensing through RTS and CTS. Right? When you send RTS, you get back. When you send RTS and then you have CTS back, in a different manner, you are still sensing the channel. But you are sensing it via access point. So different ways of doing this, either through completely DIFS or RTS and CTS. Then another term that you should know is NAV, which is mentioned in the RTS value. When you send the RTS frame, you send a network allocation vector which is asking for amount of time that you want to reserve the channel for. And so if you want to send 10 data frames, you will ask for time or NAV value which is 10 times one data frame. Right? So that now access point, if it says clear to send for 10 times the data frame, you can now push 10 data frames in succession. And then after that, another node will get a chance. If you request for a very long NAV, right, access point might reject that request because then you are hogging the channel. So, but you have an option of saying I want to transmit 1 frame, 2 frames, 10 frames, whichever number you want, and you will reserve the channel for same amount of that. So let me, okay, this is all clear. So you know this part. Okay, let me see. So we define a basic service set. So this access point and the nodes connected to this access point is one BSS. Do you know how many access points we have in the campus? Any guess? What is your guess? What do you think? This room has got about 4, right? So overall, how many access points would we have? What do you think? It's very close. Yeah, it's 125 or so. So, right, so we have about that many access points, right? So every access point has its own BSS, the nodes connected to it. Right? So that is one BSS, and we have about 120 BSS, and then we create something which we say ESS, extended service. So throughout this, if you put together this 125 odd access points, right, we have one ESS. Because you see the student network is here, it's there on the floor above, all the floors in fact, and everywhere in the campus. Right? So you are getting an extended service throughout the campus, which is this one. Okay? So that's what we said, overlapping BSS will form one ESS. So within the campus we have one ESS. And then there is a distribution system, which is the backbone network, which is wired Ethernet in our case. So all these access points, and 120 of them, are connected to one wired network. And that's our distribution system. That is how to distribute the network. And all the access points are connected to that. So if one access point wants to talk to another one, how would it talk? How would one access point, in our case, let's take example of our case, what is happening? If one access point wants to hand over one client from here to here, they have to communicate. How would they communicate? Through Ethernet, right? But there is now a latest technology where they have another antenna, right? And they don't. Then you don't really require this Ethernet. They can directly talk to each other. Also, but nobody is master and slave here, right? So that is acting like ad hoc mode, and this is infrastructure mode. So they talk to each other through ad hoc manner, directly through the radio. Right? They don't need to use a backbone network. So that's the latest one, but in this course we are not going to touch that. Right? We just use the old one, where we use an Ethernet line to connect all these access points together, and they talk to each other via that. All the nodes within one BSS are synchronized in time. And that's one hard thing. Which means, see, why do you need to synchronize the time?
If the device moves from one area to one network, one BSS to another, the data should be synchronized. If it is 30% allocated here, then you another BSS, then further products.
Right. But so before moving from one BSS to another BSS, right? Even within one BSS, this is AP and these are the clients. Right? These are client nodes. All of them should have the same time. That means when I say this AP, and this is synchronized to AP, right? It's not synchronized to anything. So AP is the master here. Right? And so that's why it is constantly sending beacons to synchronize. Okay, let me touch upon the latest thing. Do you know what is the latest technology in iOS 8.1 and macOS 10.10? What is the single biggest technology that came out through this release? Have you heard of this one? Has anybody heard about this one? Let me digress for a minute. You haven't heard about this one? Anybody? You heard about this? What is it? Right? Right. So that's one. If you can resume your work somewhere else, what is the other use of this one? Where people will probably use it more. So if I get a voice call on my phone, and if I'm working on my laptop or a desktop or a computer, and the phone call automatically comes on the machine where I am. If I'm using my iPad, it will come to the iPad. Right? If I'm using my desktop, it will go there. Wherever, right, it will be handed off to that other machine. So, what is the technology there? How is it being used? What is it? So, Apple did something in Wi-Fi, and they realized it totally through Wi-Fi. So, one basic thing that you require is they must be connected to the same access point. Two devices must be connected to the same access point. That means my laptop and my phone should be connected to the same access point. Then and then it will work. Otherwise, it will not work. Okay. So what is happening? Think what Apple engineers must have done to realize this solution. Think about this. You know Wi-Fi now, right? And I already told you what is this handoff. So the thing is, the phone gets a call, right? There is an access point here, and let's say this is my laptop. Right? So how would you do it now? You know networks, you know all socket programming, you know what CSMA protocol is, you know how they work out. So now you tell me, how would you solve this feature? Think about it. If you want a couple of minutes, you just take 2 minutes and tell me how would you do this. It's not hard. Yes. Yes. Let me take it back. That's a good question. I think for now, see, if they are on the same, it will certainly work out. If they are not on the same, it might still work out, but you need to know now the way IP addresses are assigned. I am now giving you a solution also. Right? Okay, so let's assume they are on the same SSID. They are on the same SSID. That means you also are connected to student M or N, and this is also connected to student M and N. Then how would it work out? So what happens? Let me give you a few hints. When the call comes, it comes to the phone. What should phone do? Other than ringing, of course, it starts ringing. Yes, it connects to the AP, right? And
establish a connection with that particular device, transfer the particular phone call from it to laptop.
right, but that could be little last moment thing, right? I mean, you start this discovery at this time. This is something called the discovery. You're trying to find out the laptop at the last moment. It could be little late because the whole communication might take long time and the call will just go away because you know internet and all the communication takes time, right? So you can beforehand do some preparation. Already registered, right? So what you do is this laptop and this phone, right, will get registered somewhere. And that's where they use this iCloud service. They have a system called iCloud. So you log in using your iCloud account here and here, right? So then there they note that this and this device is in the same BSS, because they can see the MAC addresses and they know the IP address of each other. See, discovering dynamically IP address of somebody else is really hard. Okay, because you don't have a DNS system. You know all DNS. What is DNS? Right. So beforehand, they populate in the iCloud system that I am this phone owned by this person, and this laptop owned by this person. I'm in this BSS. I'm in this BSS, which is matching. Right. So there is an opportunity now to do the handoff. Okay. So now when the call comes, phone will get this information already from the iCloud service that this is another node which I can hand it over to him. Right? So it knows the IP address. So it can then create a network connection between these two because you know the IP address. And you wake up this guy saying that there is a phone call. Right? And if this guy accepts the phone call, now the call will be coming through your GSM network to the phone, through Wi-Fi, through the AP, through the laptop. And then this is how the connection is established. So access point is now doing the routing. So locally now you are routing the call through access points. Yes. Right. So at that point the call gets dropped. If both the devices are mobile, typically it will change if you move from one access point to another. In our case it doesn't, but in some networks it will. In that case, the call might get dropped. Right? So that's why they say you also switch on Bluetooth to verify whether they are really close by or not. Right? So Apple says switch on your Bluetooth also, right? And your Wi-Fi should be on, and you should have an iCloud account, and with all that, this will work out.
So considering that we're using the centralized iCloud system to register the MAC addresses, we have multiple APIs and multiple devices and a central basis, a central. So there's a network and the devices are multiple APIs. So why won't communication be possible there?
You're saying this laptop is connected to some other API.
Some other API. So
See-
problems in that
See, okay, so if this is AP, let's say, is owned by some another institute, that's it will not work out. Why wouldn't it work out? Right. So this phone has to connect to multiple things to another network, right? And that is not guaranteed to work.
I'll say in the same network, there are multiple APIs.
See, it will. See, this is one AP is doing the communication, and that communication is easy to do because you know the IP addresses. If you are on the other network, right, it might still work, right? If we have this routing in place, within one AP there is no routing, right? I can talk to the another node very easily, right? AP is not going to block that. But if it is multiple APs, then you have to place this routing entries and tell APs to send it to and so on. That may or may not work. If you have it, it will work. If you don't have it, it may not. Yes. Yes. So if the routing entries are correct, it will work, but then the iCloud should also be, Apple should also be ready in their code to allow it. Okay. So there is Apple specific thing, but technically it will work if the routing is in place. Now one thing is it requires time synchronization. See, you want to make sure that these two nodes are in the same BSS at the same time. If my phone is here yesterday, my laptop is here today, right? These two entries cannot be matched, right? In fact, the accuracy that they want is less than a minute. Right? So these two nodes are time synchronized with an accuracy of less than a minute, and that's why access point provides this for another thing also, and that's why they need to be synchronized. And the only way to synchronize is you keep on talking to each other, right? It's little. All the devices, everybody will ring up, right? It's that Iron Man movie, right? You see all these coming together, including phone. See, that device, no device really knows where you are. Right? So everybody will ring up. You have an option to disable things and not let iPad ring up. Right? Because how do you really talk on an iPad? Okay, so, but everybody will ring up. Okay, now coming back. Right, so this is, see, you see these technologies are really being used. It's not there in Windows, it's not there in Android. There is a startup which is doing it for Android. Google has left it, it actually has fallen back. Okay, so the reason to synchronize is there is another thing which we say point coordination function. Other than distributed coordination function, we also have a point coordination function called PCF, where access point asks every node that which node wants to talk, and then it decides using TDMA, not CSMA. It uses TDMA for every node to talk for some time, and then the chance goes to another node. So your access point is capable of doing CSMA CA and also TDMA. Right? It polls every node and asks, okay, how much data you have, how much data you have, how much data you have. Then it decides on a schedule or a timetable. So you will talk first for 10 minutes, and then you will, and then so on, right? And that's why every node has to be time synchronized, because for TDMA you need time synchronization. Right? So you can so the nodes can either use this one, ECF function, or DCF. DCF is fully distributed, and everybody gets a chance. You have to contend. You have to compete to get the network. Here, you give a request to access point. Access point decides it and gives it. Right? So this is mostly used for connection oriented, like voice and video services. So now, can you say how much would be the throughput for 802.11? Right. So the last question now is, you have TCP, you have IP, and then you have this MAC layer, 802.11b MAC. Right, so that's one protocol. This is another protocol, and that's the third protocol. So how do these protocols sit on top of each other? What is happening? If you revise or remember from the networks course, you get the TCP segment, you give it to IP layer. What does IP layer do? It adds something on the top and on the bottom, header and footer, and becomes an IP datagram. That thing goes and comes. This is what you have here, application data. Then you have something like this. And then you take it and you make it bigger. Right? And then you take it and you make it still bigger. Right? So if you now look at through the pipeline, what is happening is your small data is getting fatter, fatter, fatter till it reaches the frame and it becomes a frame. Right? And then it sends out. So this is where you have TCP. Right? This is the IP part. And then the rest of it is MAC. This is data. This whole thing is TCP. This whole thing is IP data. So when I say 11 Mbps at this layer, I say this is 11 Mbps. What is your application layer throughput? Throughput for this. Is it more than 11 Mbps or is it less than 11 Mbps? Or is it equal to 11 Mbps? So application layer throughput is where this is the throughput, right? Data coming from the application. Right? So at what rate application layer throughput? How many data bits per second are going there? Is it more than 11 Mbps or is it less or is it equal to 11? Less than. Because this gets added and added. So every one bit overall will have more bits. Right? So that's why actually when you send 11 megabits in a second, the real data within this from the application is far less. Right? So that's why you buy a box and it says 11 Mbps, 54 Mbps, 256 now or 300 something, right? What you get finally is way less here. Right? So that's what you are interested in yours. So this slide actually takes the whole thing together now. TCP, IP, data, frame everything together, and it tells you what is exactly you are getting. When you send a TCP segment, what do you send also? Anybody remember this TCP? Window system, sliding window. So what is every TCP thing also contains? There is also an ACK. And ACKs are going both ways. Right? So the way it's happening is, in TCP you send a data packet and it's followed by a TCP ACK. So is a TCP ACK? How would you send a TCP ACK using 802.11? Or let's take a simple question. What is the difference between this ACK and the 802.11 ACK that I showed you? So I said at MAC layer there is an acknowledgement, and I'm saying at TCP layer there is an acknowledgement. What's the difference between these two acknowledgements? Is it the same ACK? Do you remember that there is an acknowledgement at TCP layer? Is there acknowledgement at IP layer? There is no IP layer acknowledgement. You send it and it's best effort. You forget about it. TCP gives you reliability, and that's why it has an ACK. The question is, what is this ACK and what is that ACK? What is TCP ACK? What is 802.11 ACK? And what's the relation between these two? See, this is where it starts getting confusing. When you put together all the things together, right? You, for the first time, integrate all together, right? Things start breaking. Because you have to think about this. Good, right? So one difference is you're saying is the ACK at the MAC layer is between access point and your client, and the TCP ACK is between the server and the client, which will be very far. It's not in between the routers. It's not this access point. It's really the other end of the network, like Google.com. It's coming from there. Okay? Now, how would you send that ACK, TCP ACK, using MAC layer? Next question. So this ACK is different from this, we know this. Now how do you send this ACK? All you have is the MAC protocol, right? You have to talk to the access point first before you send it to Google. So that's the example. And my phone is ringing and my laptop is ringing. So how do you send this? You get an ACK of TCP and you want to send it to the real server, which could be at the other end of the world. How would you send using 802.11? All you have is 802.11.
Already
Yes. So this will be a MAC data frame. And you take this ACK, right, and it's the data for the access point. It's not a control frame. It's not an acknowledgement frame. So it has to work like data. Okay. So you first send the data. Then how much time do you wait for? SIFS time. You get back ACK from the access point. It's fine. Then you wait for DIFS amount of time. And then you take this TCP ACK. You send it. How much time do you wait now? SIFS or DIFS? It will be SIFS. Let me show you how it works now. Right? You send TCP data. You send TCP data, then you wait for SIFS. You get back an ACK. This is the MAC layer. Then you wait for DIFS again. Good. And then you send TCP ACK, which is a data frame for the 802.11 layer, right? And after SIFS time, you get back an ACK, which is the MAC layer ACK, right? So the protocol TCP/IP works like this using the MAC layer. You send TCP data. After SIFS time, if everything is fine, you get back a MAC layer acknowledgement. Then you wait for DIFS amount of time as a CSMA protocol, and then you say TCP acknowledgement as a MAC layer data frame. For the MAC layer, it's data. It doesn't recognize this ACK. This has to go somewhere else, right? And then after, if that goes through fine, after SIFS time, you get back an ACK from the access point. Okay, that's fine. I receive it. Right? And that is how everything goes fine. Right? At any point in this, you get a collision. Right? The back of algorithm kicks in, right, and it delays all the things. Right? So this is how the TCP IP will sit on top of MAC layer, and it will use MAC layer data frames to send only MAC layer data frames. Okay, it cannot use MAC layer control frames because that's the property or proprietary thing of the MAC. Okay. Is it? What is any questions about this? So all these ACKs can get confusing because there are so many different types of ACK. An ACK at one layer is data for another layer, the layer below, and so on. Right? ACK for one layer is not an ACK for another layer. It looks at it as a data point. So, and they have done the calculation. Right? So you can go through this, like I explained the same thing, it's mentioned there in the slides. And after all of that, they will see that if you have a payload of 1460 bytes, right, then with TCP headers of 40 bytes of header of TCP, it will become 5.50. Typically, all Ethernet frames are of this size, 1400 and 1500 in that range. Right? And then you add the header of MAC layer and everything, it becomes 1536 bytes. Right? So finally, it becomes 1536. Actual data is less than 1460. Right? Because there is HTTP header also there. Right? And it all goes down with this, right? And without any backoffs and so, if you do the calculation, right? If you do all this calculation of SIFS and GIFS, then the acknowledgement packet is 14 bytes, and you do the computation, right? It takes TCP data packet will take 1573 microseconds, and TCP ACK packet will be 511 microseconds. Right? So that's the time thing you are talking about. Your 1500 bytes actually are taking 1573 microseconds over the air. Right? So it has to be very good time synchronized. Right? So overall, now if you do the computation, what you get at the TCP layer is 5.6 megabits. You take 11 megabits per second network, use TCP on that, you get 5.6. Right? It actually is almost half. And you divide it by 2. If anybody gives you a network which is 100 Mbps at MAC layer, at TCP layer, what you are getting is it's less than that. Right? Then they do the same thing for G. Right? What is the maximum speed at G? For the G network, it's 54 Mbps. Right? If you take 54 Mbps and right, you take all the computation, what you finally get is 27 Mbps at TCP. So these are less. Questions? So you can look at this computation, how they have done the addition. DIFS time, data time, SIFS time, ACK time, add up all together, it's 322 microsecond for the data. Right? And then you can do the computation. So I read in the article that what is the data rate that our PM is getting in his office. Did you notice it? 35? So there was an ITF file which asked how much is the data rate for the PM at his office, his own office. So look at it. Right, so you will understand what is he getting there. So you can go through the same calculation of RTS CPs. I'm not going through the calculation. The takeaway is you should know what is the CSMA protocol, what is DCF, what is PCF, what is RTS, CTS, and what are these delays that you incur when you take the TCP protocol and push it through the MAC layer protocol. Okay? MAC layer will add its own overhead and it will slow you down. Right? And how much is this slowing down you get when you transmit it through this one? Right? So this one you see, it is giving you 9 Mbps or so. Right? Every protocol will tell you how much overhead and how much is the speed that finally you get. Okay. So take this one. Questions? Okay, so before we, so this is how the frame looks at 822.11. I showed you this one, right? So this is its structure. The thing that I'm showing you here is here. The payload is here. It could be 0 to 2312 bytes. Typically it is 1450, 1460. And you set it up to be 1460 bytes, and that's how much you put as a payload. There is a CRC check at the end. You see if the frame has bit errors or what. And this is all of its header. We have control frame duration address 1, 2, 3, 4. The interesting part between wired Ethernet and this one is this has got 4 address fields. How many address fields typically you have in the Ethernet? 2. Typically in any network protocol you have 2 address fields. You say source and destination. This one has got 4. And that's a separating factor. Now, why 4? The reason is the first two are what you do, source and destination. The MAC address of the host or AP is receiving the frame, MAC address of the host or AP is transmitting the source and destination pin. Right? That's the obvious one. But what about these two? There are 2 more address fields. So the reason is Wi-Fi network is different from wired networks. Wi-Fi networks is typically used like this. You have this DSS or ESS, and then you have a router, and then you connect to the internet. Right? You do not connect directly to the internet using your AP. Right? I don't connect this network directly to BSNL network through the same internet. Right? We will have a modem in between, DSL modem or somebody in between, your cable modem, your DSL modem, something, some broadband connection. Right? That's this router. So if this node wants to send data to the internet, what should it do? I showed you this diagram, how it works out. I showed you the thing about the data and the add. Right? But what about the addressing? If I want to send data from here to here, how do I tell the network that the data should go there? Source address is this, let's say this one center, H1. MAC address source is this H1. Who is the destination address to field? AP. AP is MAC address. Okay? But is this really for the AP? See, this frame it's not for the AP. I am sending it to the internet. Right? AP is just to give you wireless access. Right? I'm not going to comment. There are no websites on the AP. Right? Facebook is not on the AP. Right? So this should go somewhere else. How do you tell AP that it's not for you? Right? It's for somebody else. And that's where you use the third address field. So you tell AP, this is for you, and you send me back a MAC layer acknowledgement immediately if you receive it. But if once you get it, you have to send it to this router. Next one. Okay? So this is a subtle point. The point is, you give this data frame to the AP. AP should send you back after SRFS amount of time one acknowledgement saying, I received this frame. So AP should not sit on this data frame. Right? Its job is to give it to the next one in the network, this router. And this router knows how to connect to the AP. Okay? So the station now says, right, this source MAC address, destination, this is coming, right? This is the source, this is the destination, and the next hop address is this R1 router. Once R1 receives it, what will R1 do?
It will make an entry in its own table that I'm sending this address packet for that H1 so that when it comes back, it knows that to give back.
Right. It's not MAC this at this level, MAC is IP level. Right? So there is this MACing that happens at IP layer also, IP addresses. Right? This is happening, so R1 will make an entry that this frame is going outside. So I will receive back a response back. And when it comes, I will give it back to H1. And but it has to also do the same. It will go through the access point. Right? So the access points are doing something which is a little complicated. It is not only doing the coordination within this channel, but it is also forwarding the data to the. So that's why you have these multiple addresses. Okay, so this one, and the MAC address of the router interface to which AP is attached. So then it gets to the router and the internet. Right? And there is another address field which is only used in the ad hoc mode. I'm not going to explain it, how it's used in the ad hoc mode, right? But it's only used for the ad hoc mode. Okay? So this is not traditional, it's very unconventional. We have 4 address fields in the frame: source, destination, next hop, and something for the ad hoc. Right? We use a combination of these 4 ones to do the communication. And so the wireless, as you see, is now expanding. It can do handoff of a cellular phone call today. Right? Very soon, you can envision that if anybody calls on the landline, the call can actually land upon your laptops. Right? Today, it is happening for the cell phones. Very soon, for the landlines, also it will work out. Right? If it is coming from the landline, right, you can even route it through the Wi-Fi to your desktops or iPads or anywhere. Right? And that whole thing is being used for Wi-Fi. So I'm going to stop the MAC layer protocol here. The next thing that is people are working on is the HD, 82.11 HD mode. So HD means that it's a high density mode where a lot of people with lots of big devices, also laptops, retina displays, TVs, everything. Coffee machine, everybody is now talking on Wi-Fi. And there are coffee machines which can talk Wi-Fi. There are refrigerators which can talk Wi-Fi. There are TV already talking on Wi-Fi. And everybody will get on Wi-Fi. And the contention increases. So how do you create a protocol where everybody will seamlessly talk to each other within the local network and also to the internet? Right? So that's why this is still a very active area of research. First doubts? So now after this, we will go one layer above. We saw the physical layer, we saw the MAC layer. Right? Now we will look at mobility at one layer above, right, which is the IP layer. Okay. So what is can you give me an example of mobility at IP layer? See, I have given you, if you are moving within this building, you are mobile, but you are in the same ESS. You are still within the campus. Right? This is the example of it. You talk to one access point, go to another classroom, talk to another access point. Right? But there could be overlap, or at least the backbone network is the same. So you can communicate like this. Can you give me one example where you have mobility at IP level? You were asking questions about this. Yes. Right. So that's one way to look at this problem. Your IP address is not changing. Right? What happens if, can you now give me a real example? You give me an example which is like a symptom. Right? But when will you see that symptom? Give me an example where this will happen. No. The IP changes. Right. So I want an example where you are mobile at layer 3 IP layer or network layer. It's not hard. You do it all the time. You go from here to home. Right? Is your IP same? Your IP is not same. Right? So when you are here, you have one IP. You go to your home, right? Then you have another IP. Or you visit somebody, there is another IP there. Okay? So your IP is changing. So that means you are mobile at the MAC layer. Sorry, at the IP layer. Okay? And how will you do the things when you are mobile at the IP layer? And that's the hard problem. You want to solve these problems, the 4G and 5G are trying to do it, right? But it's not yet there. Okay. Now that's the protocol. We will not talk about cellular because we're talking about Wi-Fi. We'll talk only about Wi-Fi. So a spectrum for mobility is low mobility, middle mobility, and very high mobility. So low mobility as we studied, right? Within the same access points you are there. Right? Another level of mobility is you are moving around in this campus. Right? So that's also mobility. And very high mobility is right, you are actually going across town, across cities, across countries. Right? And ideally what you want is that. So I take my phone with the same phone number, I go to any country and I can still receive the phone calls with the same charges. Right? That's the ultimate level of mobility that we would want. I take the same IP, I go any part of the world, and I use the same IP. I don't have to ever change it. If we reach at that point, that is the maximum mobility we can provide, right? There are no changes anywhere. And that's what we want to achieve.
Does that mean that we are just having devices with static IPs?
See, with IPv6, we have solved the problem of scarcity of IP. The dynamic IP came in because we did not have that many IPs. We really did not want to change our IP addresses, just like we don't want to change our home address all the time. Right? We don't want to change IP addresses, we don't want to change phone numbers. Even within the country, I don't want to change phone numbers. Right? But today it's not there. Right? We have to change it. Right? So finally what we want is no change in any number. Since if we have infinite number of addresses, why do we change it?
So, on that point, if we have an IP6 address for our phones,
Yes.
it will be a static address.
Yes.
It will be valid.
Right.
So it is basically like it is equivalent to static address.
Right. So the question is, so we'll look at this answer next time. The question is, if we have infinite IP addresses, I can live with that IP address all the time, then don't I have the mobility already? Yes or no? Do I have the mobility? Can I take that same IP address and live forever, everywhere? This is the question. Nobody has to take back my IP address, right? There are infinite IP addresses. And then I can just take it anywhere. I go to Switzerland, I go to US, I use the same IP. That we resolve because we have infinite IP addresses and we given this such that there is no conflict. In that case, can I take my IP anywhere? So that's a separate question, right? And it's a topic in itself. Why we have a MAC address and why we have an IP address. Let it be aside for now. But if we have these unique IP addresses everywhere, then can I go with that IP address anywhere? I think we saw this answer to this in the networks course. Routing be a problem. See, why do you, if I have a Delhi number, and if I go to another city, I go to Bangalore, and what is the challenge? Why do I give me a Bangalore number? Let's even not talk about mobile, let's say the landline number.
The initial part
Yes. Right. So the way addresses are there, right? You use the prefix of it to do the routing. And if I take that same address for somewhere else, right, it will look at the prefixes, and the prefix will not let me route it correctly. Right? So that randomness is hard. Right? But what so we have to deal with this. The question and the answer to the why is hard. If I have an address, the way we do routing today is geographic routing. We look at some prefix of it, we match it, and we send it to that area. But if I take that IP and go just any part of the world, right, my packets will again come back to my source, right, whatever my original location. I cannot change it everywhere in the world. That's not scalable. Right? So I say all the prefixes with 011 should come to Delhi, but by the way, 011 this goes to Bombay and this goes to Bangalore and this goes to US. Right? What is the point of routing? And we have so many exceptions. Right? The routing table will be huge. You have infinite IP addresses and you have infinite entries in the routing table. Right? So we cannot do it this way. So we need a protocol that will let us do it. So assuming very few people are highly mobile, right? Most of us are here, some of us are here, and really very few are here. Right? Then we can create a protocol that will cater to the needs of these people. Right? If everybody is here, it's a chaos. So the question is, you take your IP address, you don't change it, you go anywhere in the world, you still be able to do the routing. Okay, so that's what we will see in the next class. So now we have 10 minutes. Can you look at the quiz? So I have created a quiz. I know it's a little slow, the website is slow. If it works, you can try to solve it, right? But make sure that you attempt it. The 3 questions based on what I taught today.